Okay, hi everyone. So today we're going to be doing a another open source coding session. So last time, unfortunately, because I wasn't very familiar with the software, I didn't record the session. So I'm just going to be a bit redundant, but obviously not a lot of people have followed me, so it's okay. So today what I want to be doing is really just implementing a pull request to solve a bug in the meta learning tutorial of jaxopt. I'm going to explain all of that in a minute. So yeah, this is the issue I wrote. So there are like a couple of points that are wrong in the tutorial. Fabian Fedregosa agreed with the suggested fix, and it so happens that I also thought that the tutorial was quite slow, so I'm gonna also correct that. Let's first look at what exactly we are talking about here. So I'm just going to submit a pull request so on GitHub. And the idea of this channel is going to be, I think, a bit this. Is going to be to show what on a day-to-day basis, if you were to be a machine learning developer, you would do to contribute to open source. And so this is only my take on it. Obviously, I'm not the most experienced or the most brilliant open source developer out there. I still have a lot to learn. So if you have any feedback, I'm definitely open to it. I just want to show what I'm doing. I also think that's good for me because it allows me to be like very focused on like some contributions that I'm doing. So I do them in a very efficient and let's say proactive way. Whereas sometimes I just let it rot for a while, and I don't want that. So let's dive into it. So first, jaxopt is a framework that was developed by a team at Google Brain, and basically what it allows is implicit differentiation, and it allows implicit differentiation in JAX. So it's super nice, really, because what it means is that then for the types of problem which are of the following where you want to be solving, for example, a root function, so an equation where the x star is defined implicitly, and this equation is parameterized, then you can have the derivative of this x star of theta with respect to theta out of the box, and you can have it using all the features of JAX, which are, for example, is easily runnable on GPUs and TPUs, but also that it can handle pi trees very well. So I'm going to talk more maybe about pi trees afterwards. And so implicit differentiation, the reason I got into it is because I'm very interested in deep equilibrium models. I'm not going to talk too much about it, but I'm going to give you a link in the pinned comment. And today, we're not going to be talking about deep equilibrium models, but rather meta-learning, which was introduced by Chelsea Finn in 2017. And it's basically a way to train neural networks weights such that they are easily adaptable to a new task. And so this was used originally because they wanted to have such things for robotics. So here we're not going to talk about robotics. We're going to be doing like very toy examples, but still I hope that you get the gist of it. And we're going to be taking an example from this original paper, which doesn't use implicit differentiation. It uses classic backpropagation. But it's this paper that introduced meta-learning really, and they introduced a task which is a task of regression on some sinusoids. And so those sinusoids, you define each new task corresponds to a different sinusoid, different in the sense that it might have a different amplitude and a different phase. And the paper that uses implicit differentiation for meta-learning is this one, meta-learning with implicit gradients. I think it was featured on Yannick Kilcher, by the way. So I invite you to just check out the video. I don't remember the video exactly, but I think it explains it relatively well. So I trust Yannick Kilcher to do a good job of explaining a paper well. And so it's by the same team, and in this one they basically use implicit differentiation rather than classic backpropagation through the iterates of gradient descent. This way you can have O of 1 memory requirements for your meta-learning training. So yeah, I'm gonna first make sure that all of these are in a comment. So this is the take paper. This is the jaxopt paper. So yeah, I don't really know how to use Twitch to the best of its ability, so maybe I'm doing it a bit wrong, but if I do, please let me know. Up. Okay, I'm gonna pin that tag. Okay. And so yeah, the idea of the tutorial in jaxopt is basically to just reproduce the results of the implicit meta-learning on the sinusoid task. And so the situation before, if I open it from before, so here I just switched to the main branch in order to have the notebook that was on the main branch. I'm just gonna check, yeah. And as you see, I'm using VS Code. The main reason I'm using VS Code is because it has this thing, GitHub Copilot. It just works amazingly well for me. It really reduces my scaffolding, my testing workload a lot. And so it allows me to focus on the very difficult things such as modeling, debugging, which are really what I spend most of my time on. But all of the points where I just type stuff very robotically, most of it is handled by GitHub Copilot. So I think it's an amazing tool, and it's definitely the reason why I switched to VS Code. So yeah, in the original tutorial, the main points were that basically it doesn't solve the same task. So as you see here, the sinusoid is using phase as a frequency, so it's not correct. It should be x test minus phase, for example. The second point is that it uses a fixed amount of tasks. So here in this case, the n tasks is 4, as you see here. And so it means that overall, the network is being trained with 4 tasks. So that's just not enough to train your network. You should train with, in this case, an infinite amount of tasks. So what it just means is you just generate tasks on the fly. And the final thing is that here, the computation of the outer loss is done with a for loop rather than a vectorized map. And so which is called a VMAP. And so I think it would be much faster using a VMAP, and so that's what I'm doing in the corrected version. So I'm going to switch back. So unfortunately, I've done a lot of this work already in the previous stream, which wasn't recorded, unfortunately. So I'm not gonna just redo it. But I'm gonna explain what I did. Okay. So the first thing that I did was to correct the phase problem. So it happens in quite a lot of different situations. I think I might even need to check, because it wasn't used as like a factored function. So I might need to check if there are like other cases where this occurs. The other thing is that I created a function, generate task batch, which generates a meta batch of tasks. And so it does so in a vectorized fashion with jitting. So all of that, I'm not going to get into the details, but it just means that it's going to be faster. VMAP is going to be faster than a for loop, and jitting is just going to make sure that the code is compiled rather than just interpreted on the fly. And here on the VMap, you will notice that I'm using the in axis, which really means that I have a lot of common parameters between all the executions of generate task. It's just these keys on which I'm going to be iterating on the first axis. So it's very convenient to have this in axis. It means that you can share some parameters, some not. Very convenient. And so yeah, here I was thinking that I needed to check this generate task batch, and I think I'm going to do it right here to make sure that yeah, it's it works as I intended to. So okay, I'm basically going to replace this data tasks. So I'm going to say that data train is going to be this. So and I'm going to use n tasks here. And underscore tasks. You see here, like GitHub Copilot, it knows the variable name better than me, so it's super convenient. So here I don't need the keys. I just need to make sure that I have the face. So the face is going to be face of task, and the amplitude is going to be amplitude of task. So that's the only two things that I need for this one. Okay. So I'm just going to restart the notebook just to make sure I have everything. Okay. So here I'm not going to like use this magic because I just don't need it. It's only useful on Colab. So here I'm going to dive straight into the imports. So yeah, TPU not found. Unfortunately, I don't have a TPU on my laptop. Maybe one day I will. Okay. So here I'm just defining the functions. Here I don't need that one. And here we go. This is the moment that I'm going to test something for the first time. So here it didn't work. So it didn't work because it said too many indices for array. It still drew something. I'm not sure why. So it might be that what I'm returning here is not what I would like to. So I guess, oh no, I know why. So here, oh, okay, I think I know why. Because here I think that here those are the tasks. And here it's rather tasks of task of 2. Yeah, I think that's the correct way to do it. Because here phase is going to be the second one, and amplitude is going to be the third one. So it's tasks of task 3. I think that's it. And that's not it. So maybe I'm mistaken about what's task. Task, what type is it? It's a tuple. So I was pretty sure about it. No, actually, I didn't think it's going to be a tuple. Okay, interesting. So if I do tasks of 2, get 4 numbers. Yeah, I think here I'm just gonna do this, but with a different number, because here, because I'm returning like 4 things, if I use n task is 4, then I might be confused about which is which. So I'm just gonna do it with 3 and make sure I understand exactly what it returns. And so here it's len task is 4. So it's I'm indeed returning exactly something like this for tasks. So it means that I was correct before. But here I don't understand why then it's not working correctly. So it's as if phase. All right, I understand. Of course, it's because I'm reassigning. It's because I'm reassigning here. That's the reason. I'm doing phase of tasks. So I'm just selecting it, and at the next iteration, phase is not the same one. Okay. Okay, so I'm just gonna do something a bit dirty. Here it's all right. I'll check with Fabian if it's all right to do this. Here, yeah, there you go. There you go. Okay. So we got different phases, different amplitudes. That's exactly what we want. And then we can basically replace this. So enumerate zip of data train, data test. Repeat, added too many parentheses. And I think, okay, too many values to unpack. So here, enumerate zip. So enumerate is gonna get I and then something. And data train, okay, what is in data train? So data train, it's a type tuple. So what's the length now of data train? It's 2. So it's really X train and Y train. And so it should be unpacked as this one. So maybe the problem is if I do this, I don't get what I want really. So it's indeed a tuple. What's the length of this tuple? It's 2. So I really have data train, data test. But this one is 4. Yeah, okay. Okay, that's super interesting. I don't understand why this happens. So it's zipping two tuples because right, data train is a tuple, right? Which have length 2. Each of them is of length 2. But now if I zip them, okay, I'm not gonna spend too much time on it. Honestly, it's just something that I don't want to spend too much time on it. It's not very interesting. That's not what I want to be doing at the moment. So I'm just gonna do range and tasks. And I'm gonna go, this is this. And this should be working. Ah, no, again, too many values to unpack. What is the problem? Ah, no, of course. Of course, it's because, and this shouldn't be task. This can't be task. This has to be something, it has to be data train of 0 of task, data train of, yeah, I know, okay. Now I know. Data train of 0 of task data. So yeah, so this one, Copilot isn't too happy about it. And obviously it's because it's not written very well. Unfortunately, it's alright. I just handle it for now. Okay, so there you go. You have the exact same plot as what we had before in the notebook on the main branch. It's just that this time it's using the generate task batch function rather than looping over this generate task function, which is not what we want. We want to be like using vectorized functions, even for data generation. And so that's true for CPU, GPU. I'm not sure about CPU. Okay, so this one here is just the MLP. And so when we're doing implicit meta learning, we're really trying to solve this optimization problem. Okay, so I linked the paper in the chat, so it should be here. Yes. But I'm going to just remind everyone what we're doing. So here, basically I corresponds to one task. So it's one color here, okay? And a color really is defined by its training samples and the test samples. Even though the ground truth might be the full sinusoid, what we have at our disposal is really just training samples and test samples. That's it. Okay. And so for each I, it's a different color. It's task 1, task 2, task 3. We want to be solving a regression problem. So here this Li of x is going to be just the mean squared error between the output of our model and the ground truth. But it's going to be regularized. It's going to be regularized with a set of meta parameters. So here, theta corresponds in the implicit MAML paper to, I think it's called it's called theta bold. And this x here corresponds to phi prime. Okay? And so for each of these, you want to be solving the task of basically fitting the training samples. So for here, for the yellow curve is going to be fitting like this. And then you want to test on the yellow triangles, these ones. And you want to make sure that the test error is correct. But you want to make sure that it's correct for all of the tasks. So you want to, when I say correct, I mean as small as possible. And the model that we're going to be using here is a simple MLP. So originally in the notebook, Fabian used a swish, but this should be working even with a simple ReLU. So I'm going to make sure at some point we're able to choose between the two, but for now I'm just going to stick to the simple case ReLU. Okay. Then again, so Fabian was using a 3 hidden layer MLP, but in the original paper it's only 2, so I'm going to stick with 2 for now. And okay, I don't know, for some reason it didn't run I don't know why. Okay, so now I have my model, and so this model is going to be basically holding it's not going to be holding anything actually, because so in JAX what's pretty convenient is that you never have weights that are attached to a model. A model can simply apply a set of weights. So here x would be the set of weights that you apply on these inputs, and so it really corresponds to this very mathematical formulation that neural networks are actually a function of two things. They're a function of both the parameters and the input. And so that's really what JAX is highlighting here with this apply function. So it's very dissimilar to how PyTorch or Keras would function, where you simply you simply do model call of samples. Here you really do model the apply of the weights and the samples. Okay, so here I just defined the inner loss, which is this thing here. I defined the outer loss, which is this thing here. And I made sure that when I am defining the outer loss, I am really vectorizing the run of the gradient descent. Because here, the subtlety is that the outer loss depends on the solution to an optimization problem. So this xi of theta is the solution to an optimization problem. And that's really what we're seeing here. We're seeing here that we're computing the solution to this inner problem, so which I compute using an inner solver. And I am using these parameters to compute a prediction loss. So here this is going to be the test loss for the given task. And so this inner solver, there are like a lot of things which I define. So I'm using line search for gradient descent. I can do this because the implicit function theorem doesn't need the optimizer to be differentiable. And I'm using the implicit function theorem by making sure that implicit diff is true when I'm creating this jaxopt optimizer. Here, this is a bit complicated. Usually you wouldn't need to set this if you're using jaxopt, but here is just because in the original paper they use only 5 steps of conjugate gradient to compute the Jacobian inversion that is required in the implicit function theorem. Okay, so now we have defined everything and we should be good. So here you see, again, I'm defining the meta parameters as just the inits of this. And so now I should be able to run this. So I did a lot of to-dos because I basically want to be able to just check that everything is going all right. So this solver here is the outer solver, is the thing that's like basically learning the meta parameters. The difference between the solver here and the solver here is that this inner solver is computing task adapted parameters, while this here is computing the meta parameters. And so here I'm just using Adam as in the original implementation. So here I definitely need a progress bar. So I don't know how I usually do this, but I'm going to use TQDM. I think it's the easiest one, generally speaking, TQDM. If it doesn't work for Fabian, I'll just change it afterwards. It's all right. Okay, so I'm not sure I like how the imports are set at the moment. I don't understand them. I think I'm just gonna put it here. And I think it's from TQ. No, I think it's this. Okay, let's see if it works. Did it work? Oh no. Okay. Yeah. So I need to install TQGM, and I'm gonna make sure that it's installed here. Okay. And so now I'm gonna have a progress bar, which is going to be range of max iter. And here I think I want to update the p bar with a set description. And I think I would rather plot the outer loss rather than the gradient suboptimality. I think it's not necessarily the correct one. And I think that the state probably has it. Does it have it? I don't remember. I don't remember whether the state has. I'm just gonna check it. I just don't remember this. Okay, so I'm. Oh, that's too bad. I can't. Why can't I just click on it? I just want to click on this. Haha. Okay, never mind. I have it just on the side. So optax error. See, it has error. This optax state. So I'm just going to plot that. The outer loss is going to be solver dot. So it's going to be state. Sorry. Dot error 3f, and I can plot the gradient suboptimality, but I'm not sure it helps a lot here. So I can just rerun this. So I added a progress bar. I'm just gonna have outer loss. It's gonna be something like that as well. And I'm gonna do outer loss appends state.error, which is a bit repeated. Let's not worry too much about it for now. Okay. Blah blah blah. Okay, so oh yeah, of course. I just outer loss is actually my function here, so I'm gonna do outer losses here, and I'm gonna make sure that this is repeated here. Okay. Oh yeah, and of course I need to redefine now the function. Module is not callable. Okay, so how is TQDM used? I don't remember. Taqadum. I think it's what yeah. Taqadum. Do they have auto? Where is auto? I think it's from TQDM. It's from TQDM auto import TQDM. Aha, yes, I think that's it. I think it's better this way. Aha, yeah, it works. Okay. So it's a bit slow, and I'm a bit afraid that it's because something is taking much more time than it should. Okay, so you see the outer loss is decreasing, not decreasing. Maybe if I run it for a bit longer, it's gonna be decreasing. But it's super slow. It's extra slow. Yeah, and there is probably a bug somewhere. It's super slow, so I'm gonna check why it's taking so much time. Data start is time to time, and then I'm gonna print this. Update start. Yeah, it knows. Okay. And maybe it's the suboptimality. We don't know. It might be the suboptimality. So I'm going to check everything. Data generation is super fast, which is great. And the update is incredibly slow. Okay, so I need to check. No, the update is fast now. And so it's really the suboptimality that is incredibly slow, and I should fix this. So for now, what I'm going to be doing is a bit the lazy way to do it is I'm going to simply just comment it out because I don't need it at the moment. But I'm quite happy that I checked it. Okay. I'm gonna remove all of this. With this timing thing, I'm not sure if it's the best way to do it. Honestly, I don't have any really nice way to do it. So, up, tack, and I'm going to comment this, and maybe at some point, I don't know, like maybe I can jet it. Maybe it's the best way to do it. I can just jet the optimality. Honestly, I don't think I need it at the moment. So let's see. So now it should be extra fast. Oh no, come on. Of course, I didn't remove this. I just need the outer loss. And so yeah, the outer loss, if I remember correctly what I did like in my own work, because the reason I'm working on this is because I'm working on this for my own paper for NeurEPS. I think the outer loss should be quite small, maybe on the order of 0.05. Honestly, I'm not too sure. I would say I think it's less. Do they say that in the paper actually? Maybe they say it in the paper and I can just not check. It's the iMAML paper, not the iMAML. Because in the iMAML it's just not reporting these results. So here, quantitative sinusoid regression, and see it's going on the order of 0.0102. So yeah, we're already quite below, but of course this is the training error, so it doesn't tell us a lot. So gradient suboptimality for now, I'm gonna not care about it. And here, an important thing is that I use this thing here to make sure that I'm generating each time a new task. I'm just splitting the key that I'm passing to the task generation. Okay. So I'm going to train on a bit more, maybe 100, and see what happens. How long is it taking? I think it should be taking too long that I fix this suboptimality problem. It should be extremely fast. Yeah, see, it's quite fast. It's just not learning anything. That's the problem. Okay. So now, I can just try and see. I'm just gonna try and see what I can do. So here, what I'm gonna do is I'm gonna split, and this just reuses. I'm just gonna reuse what I did over here. I know I'm not supposed to be doing it like this, but honestly, at the moment, I would rather do something fast that works. That's something that's correct, like very well implemented. So here, I'm just gonna go for task in range of and tasks. And then this are X train and Y train. Here, it's this. Okay. And so here, yeah, he was using like these things here, but I think it's better here to just learn on this new task. So I'm just going to do these up. Okay, so here, rather than v mapping, I'm not gonna v map anything. I'm just gonna do tax like stop gradient meta params. Maybe I should keep this. I'm gonna do meta params and data train. I think it's just gonna be X train, Y train. Yes. Okay. And now, do I need X test, Y test for this? I don't think so. But it's alright. I don't care for now. Okay, let's see. Oh, right, of course. Here, I want these. I want this. Okay. So it's not that bad, as you can see. It is at least trying to fit the samples. It is trying to fit the samples. And all these tasks, we haven't used them for training. So this is all tasks that were not used for training. So it's not as in the original thing that Fabian did, which was using just a selected number of tasks. Here, every time I'm just generating tasks on the fly with different keys. So it's really not the task that I've been using for training. And so maybe I removed something. Okay. Okay, so here he was just getting the parameters and the parameters without regularization to see. Yeah, okay. Okay. So the parameters without regularization, I'm not going to show them. I don't think so. For now, let's do without. Here, what's interesting though is that, yeah, he was showing the ground truth, and I think I'm going to do that actually because I think it's interesting. I think I'm going to do that. I'm going to show the ground truth. And so the ground truth is going to be, how am I going to plot the ground truth? Because so I can get the phase and amplitude. It's gonna be phase task, amplitude task. Okay, yeah. And here I used minus for the. Did I use minus or plus for the phase? I think I used minus. Okay. Okay, and this is a minus here. Up. Okay, it didn't work, and it's because you can use J and P, I think. Okay, I'm just trying to be too quick on this. Cha-cha-cha. And the color, I think, is gonna be a problem. Maybe I can do it just black for now. Let's see. And I'm just gonna use line width of 2. line style dash dash and alpha of 0.7. Okay, and so XX is genpay lint space. And so, yeah, of course, I'm always forgetting about this. It's too bad. Never mind, I can just restart and run all. And so this I'm not going to be needing, actually. I always just basically use the same names. And oh yeah, right. I forgot to change it here as well. Never mind. Okay, so not readable at all, of course, but it's quite nice. I think it just needs a bit more training, and then we should be all set. Yeah, I think that's mainly it. That's mainly it. I think if I train it for longer, it's yeah, and I wanted to plot. Yeah, that's what I wanted to do too. I wanted to be able to plot the outer loss, so the basically meta learning curve. I think the gradient suboptimality, I'm not sure I'm gonna use it actually. No disrespect. The Y scale, yeah, why not? No, yeah, why not? Outer loss. Yeah, that's not great. It's not learning a lot, is it? And I think so. Originally, how many? So it is gradient descent with step size. Yeah, but this is the original one. I need to go into the iMAML. I'm not sure. So what I'm gonna do here is a bit cheating. I think the main reason is that originally here they say that on the sinusoid task, I think they talk about the sinus here. Do they talk about the sinus? They don't talk about the sinus. They don't talk. It's because they don't talk about the sinus in the iMAML paper. So there was actually no experiment with the sinusoids in the iMAML paper. So I'm just gonna do something that's a bit cheating, because I basically redid this experiment, so I know what I need for the sinusoid. And so the meta MLP, did I? Yeah, I think I did here. So here the implicit configuration is line search, max there is 16, max line search is 15. But did I change something? I didn't change. 70,000 outer steps. Am I supposed to be working like this? Whoa, okay, maybe. No acceleration. No acceleration. Yeah, I think the fact that it has acceleration as default is not the best. Not the best. Okay. Reg init is 2. So you see a lot of different things, because I tried, like for the omniglots example, I tried a lot of different things. Not very important for now. It's ReLU. Maybe because also the initialization is not the same. We'll check. I'm gonna check. It might be initialization. It's a bit cheaty when it's just a question of initialization, but honestly, it just happens sometimes. It's so much easier sometimes to optimize with different loss landscape. Depending on the initialize. It seems to be doing a bit better. Is it? Is it doing better? No, it's not doing better. Okay, so what I'm going to do first is just check that it's not a question of number of iterations. So here for 100 iterations, it took me 11 seconds. So I'm just going to go 10,000. It should be quite fast because actually part of the 11 seconds are just spent at the beginning. So you see here it says 11 hours. I think it's going to be much less. See here it should be done in roughly 5 minutes. And so we can already see here whether at some point there is going to be a 0 or if it's going to be just the same thing. Actually, it's a bit stupid. I'm just going to go for 1,000 at the beginning rather than 10,000 and see already if there is an improvement. If the learning curve is decreasing, then it means that there is an improvement and we can go from there and increase. If not, I'm just going to change the initialization of the initialization of the MLP. And yeah, it might be it actually. I can't see the loss decreasing here, so I might need to do just that. Yeah, I might need to adjust that. So here, the way I'm going to do this. Aha! It's a bit better. Look at this. It's much more fitting. So the MSC is like the outer loss is increasing somehow, but the results are much better. So yeah, that's a bit crazy actually, because it stopped before. And I think it's because it reached the tolerance. So there might be a problem in the error. Okay, yeah, I might be plotting something wrong, but at least it's giving good results. At least it's giving something a bit better than what was before. Okay, so I'm gonna make sure that this Optax solver, the tolerance is low. I don't know what the tolerance. It's only 1 E3. I'm just gonna go -6. Okay. So I think there is a problem with how I'm computing the outer loss, because the results are good. Like they're much better than what we see originally. So if we look at the okay, why isn't my GitHub Octo tree working? My Octo tree, where is it? Usually I have a tree here and it's not working. Yeah, it's here. I don't have it in the issues. Why not? It's ridiculous. Is it in the... Where is it? Is it in the docs? Yeah, it's in the docs. Is it deep learning or is it implicit differentiation? Yeah, it's here. Okay, so if you remember correctly in the docs, as you can see, the example with meta learning was not really working at all. Now it's just much better. It's much better. It's much better. It is much better. Okay. Okay, so that's quite nice. I'm only a bit concerned about the fact that... Okay, so I think as is, I already like the example. I think it's already giving a good example because like the end result is quite close to what you would expect from MAML. It's not perfect, of course, but it's just a question of tuning correctly. And I don't want to be spending too much time on just initializing it correctly. I don't think it makes much sense. Just because, yeah. And maybe error isn't what I actually think it is. Maybe error isn't what I actually think it is. Maybe it's value. It's value, of course, it's value. It's not error. I'm just going to interrupt this. I think it's value. It's not error, it's value. Error is going to be the gradient norm or something like that. Yeah, see, this is decreasing. Yeah, this is decreasing. Of course, its value is not error. Okay, so that's cool. So I solved this issue. As you can see here, it's decreasing quite a lot. It's decreasing quite a lot. And we're gonna see this even in the meta learning curve. And it's quite fast. So even if I do 10,000 and I reach like 6 minutes, but I think it's cool if like the notebook runs in less than 1 minute. Maybe on TPU it's gonna be even faster. At some point I will need to test this on TPU. Aha, at least I have something. At last I have something that's decreasing, and it's giving me the good results. So they're fitting. Maybe for the legend I need to improve on it. I will see with Fabian if it's really necessary. I think this is very, or this is already quite telling. So I'm not sure I need to do much more. Okay. Do I have some extra stuff? Okay, LBFGS, I would rather not use it, honestly. I think it complexifies the stuff without a lot of help. This I don't need. I think I'm gonna just remove this, honestly. This gradient suboptimality is not needed. I don't think it's needed. And anyway, I can always re-add it, it's fine. I'd rather send something in the PR that's very clean. Doesn't have too much GitHub Copilot prompt. Yeah, the swish, honestly, I'm just not going to keep it as well. I think this should be a simple thing. People are just going to play with it and adapt it as they want. Okay. And now it has the correct outputs. Yeah. Yeah, okay. I think I'm quite happy about it. I'm going to save it and I'm going to submit the draft PR, and I'm going to see how to test this on... So GPU is going to be a piece of cake. It's just so easy with jaxopt and jax. TPU, I have never done it, so I don't know. Okay, what did I do in my log, by the way? So what did I do today? I basically corrected loss computation, corrected plots, and that's it. I didn't do much, honestly. I didn't do much. I just corrected the plots. Yeah, maybe acceleration, but I think it's a detail. And the loss computation. I think that's it. I didn't do much. I think it's mostly it. Prof. Okay. Okay. So I'm gonna create a pull request. Fixed the iMAML tutorial. Basically implemented the correct training setup. Yep. So corrected phase in sinus. Made sure to use more than 4 tasks for meta training. What had I written? DJ. And yeah, used VMAP for outer loss computation. Ah shit, there's a pigeon on my... Yeah, okay, it's gone. There's a pigeon on my window. Okay. Then adapted all the plots. TPU testing remains to be done, and so I'm gonna create a draft PR at Fabian Pedregosa. Oh, sorry, I'm gonna say that this fixes 417. Don't hesitate to tell me already if some things should be improved with respect to, for example, using LBFGS as the inner solver, a more complex MLP with swish activation, or yeah, I think so. Okay, tag. Okay, so how long have I been doing this? Yeah, 1 hour. So aha, they want to offer you a promotion, blah blah blah. Pfft. Oh, okay, so it's just a shitty spam. How can I remove this? Can't I remove this? Okay, I would love to be able to remove this. It's alright, I'll check it later. Okay, so yeah, I think I still want to do the TPU stuff, so I'm gonna try to do it on TPU. Okay, I think there was an easy way to do this, so I'm gonna go on my fork. No. I'm gonna go in the docs, the notebooks, implicit diff, MAML. Wait, what? Oh no, because I'm not on the right. Oh no. And no. I'm not on the right branch. Yeah, that's the right branch. So now if I just click on this, does it work? Nah, it doesn't work. Too bad. But maybe okay. I think normally it should be pretty easy to open something in Colab. Yes. Okay. So now I want to open something in jaxopt, paf. The branch is not the main branch, it's the fixed MAML example branch, and it's the MAML, paf. Okay, there we go. So first question, does it run? Execution. Execute. Ah, it's Control F9. Okay, let's see. I hope it doesn't have a lot of mistakes. I think it should be working all right. Especially since now I'm just on CPU and I've been testing on the CPU all the time, so I don't see why. I don't see why it would be doing something wrong. Okay. Okay. It's on the difficult part. It's training. It's doing the meta training. No, it's just initializing the meta parameters. Oh no, the state of the outer solver. Aye. I think that's quite a nice feature from Colab to have like this green arrow. It helps you understand where you're spending most time. So even if you don't have like your the profiling like I did, like it's still something that like allows you to see where you're spending time. So here, yeah, it's about 1 minute. So I think that's what I was expecting. Same as like my computer is probably quite more efficient than Colab. Still, it's alright. I think, yeah, 1 minute is alright. Yeah, I think Fabian is going to test it anyway in terms of runtime. So if it's too long, he'll just tell me. And then we need to modify type of execution. I am sorry, this is all in French. Hopefully you can just translate. It's just it's the same order of tabs, honestly. So it's a file, modify. How do you translate that? Yeah, anyway. And this is run, tools, help, insert, and broadcast. Okay, nice one. It's the same things. Obviously, because of the C, it's going to be exactly the same thing. That's what's cool about Jax. Okay, so now, what about GPU? So yes. So okay. I'm gonna check when I arrive here. That's indeed using GPU RAM. Otherwise, it's a bad sign because it means that it's not using the GPU correctly. I think it is. I tried like on the same, not the same version, but this example that I implemented differently. So it's using GPU. I think it's using it correctly. It's booking a lot of GPU RAM. That's just insane. Like, so with these Google products, they basically grab the whole GPU for themselves. I have no clue why they do it like this. They probably have good reasons, but I don't understand why they do it. Because this is very, very far from 11.5 gigabytes. Like it doesn't use 11.5 gigabytes. So it's a bit faster. So that's quite nice. Yeah, it's twice as fast. The main thing here is the compilation time. Of course, it's very, very slow at the beginning. And then you see it's lightning fast. So yeah, we managed to make use of the GPU. So that's quite a nice feature. Hopefully, it's going to be the same with TPU. Aha, quite nice. Okay, cool. And yeah, I think it's relatively the same thing. Yeah, super nice. So it means that the GPU doesn't add a lot of stochasticity. Okay, now TPU. What about TPU? Wait. Okay, no, perfect. So on TPU now, I don't know how it's supposed to work. Because I've used it before for like some Keras stuff, and you're supposed to connect to it. It's very complex. But if I understand correctly, with Jax, it's supposed to be seamless. Let's see if it's seamless. I'm not sure it's seamless. Aha, already. So it's not seamless. TPU not found, continuing without it. Why? So, if I try this outside. partially initialized module Jax has no attribute version. Mostly likely due to a circular import. Okay. What is it? Control MD. Okay, so that's a problem. Why? Okay, I'm just gonna restart everything and execute everything. And so I think here it's still, yeah, it's on TPU. I'm not gonna spend too much time trying to fix this. Like if it fails, I'm just gonna copy paste the error, try to see if it exists in Stack Overflow or elsewhere. And if I don't find it, I'm just gonna say to Fabian, ah yeah, okay, look at that. Partially initialized, Jax module has not attribute. Okay, so did you restart your notebook session? Yeah, I did. Okay, so Jax and jaxlib are out of sync. Okay, so I'm gonna do pip freeze grab jax. And so, yeah, those are the two versions. And so, jaxlib compatibility matrix. Maybe I just need to reinstall jaxlib. Pip install -u jaxlib. I don't know. Is it that? If it's just that, it's stupid, but. Restart runtime. And I'm going to do Control F9 now. Add TPU in front. Any people ever reported that? Nah. Okay. Aha! TPU not found, though. So that's a bit shitty. Why is it not found? I am using a TPU. Okay, I'm just gonna quickly Google Jax use TPU. Use TPU collab. Haha, I want to use TPU. Jax CPU wave equation. Okay, so they do Jax, blah blah blah, Jax. Okay, let's see. But actually, let's see what it tells me, right? Because it's supposed to be telling me something here, I guess. Runtime error. Only TPU VMs. Recommend trying Kaggle notebooks. Oh no, I'm not going to do that, so I'm just going to explain. I'm just going to explain to Fabian that it doesn't work because of this. Okay. Okay. So that's it for this PR. I'm just going to write this. So I'm gonna say, unfortunately, I cannot test on TPU on Colab because they are not supported anymore. Would you like me to test on Kaggle even if the quick button still points to Colab? Okay. Yeah, too bad that we can't use TPUs on Colab now. Maybe I'll try on Kaggle at some point, but not today. Would you like me to test on Kaggle even if the quick button still points to Colab? Yeah, that's it. I think you will understand. And I think I'm gonna mark this as ready for review. Otherwise, oh yeah, I'm gonna say otherwise tested on GPU. It is twice as fast. So working, I'd say. And I'm gonna mark it as just ready for review actually. Okay, that's stupid. It's in Python, but it's not Python. Okay, ready for review. Okay, so that's it. You saw basically the end. Unfortunately, you didn't see me coding a lot and spending time on like trying to debug. There was a little bit of debugging. Yeah, overall, I'm quite happy with the result. Especially, I'm quite happy that basically there is something very visual at the end. You see, okay, it does look like the model is trying to learn something. Maybe we can push it a bit more. I don't think it's really the goal of this tutorial here. The goal of this tutorial is really to showcase how you would use jaxopt. And basically, I think that what is really important to notice is we can use this gradient descent here and just say implicit diff is true, and then you have implicit differentiation out of the box. What's more, you can also use it on the parameters of the network as if it was a vector. How can you do that? So you don't have to you don't need complicated functions that map your parameters to a vector, then from this vector back to a list or to a dictionary. You just use these three util functions. They are super, super useful in order to make sure that you can apply functions to PyTrees, which can be like dictionaries, lists, as if they were a vector. So that's incredibly useful. So yeah, those are the two main points I wanted to showcase for jaxopt. I really love jaxopt as a library. I've been using it quite a lot recently for my own work. I was really lucky because I got invited to the sprints early this year, and like the people at Google were really welcoming. So I really thank them for that. And I hope to be I hope to continue working on the library. The other issue that I'm going to tackle soon, it's a pull request I'm actually doing at the moment, is trying to implement the Broyden method. Super useful for deep equilibrium models, but at the moment it's not working for some stupid reason. It's working in float 64 and it's not working in float 32. So we need to check that. So that's going to be the next PR that I'm working on, and I'm going to be live streaming on Twitch. Okay, so it's going to be the end of this stream. Hopefully this time it recorded it, and yeah, see you next time.